When we're thinking about gravity, it is very easy to fall into this misconception where we think that gravity only describes things falling down towards the Earth, where the only possible demonstration of gravity is that it pulls things downwards towards the center of the Earth. But this is not true. Gravity is much more than that. The idea is that any two objects that have mass will automatically experience gravity. They will have a pull on each other. And this is described by a formula, and we're going to be looking at this formula. So to make this idea closer, think of how the moon is revolving around the Earth, and the moon is experiencing its own weight due to the gravity of the Earth, and it's revolving around the Earth on its own orbit. So, given that the Earth is able to apply a force on the moon, what's stopping the moon from applying a force on the Earth? The answer is nothing. The Earth experiences, and according to Newton's third law, it experiences an equal and opposite force by the moon on the Earth in the opposite direction. And this is also the weight of the Earth in a sense, as the moon is pulling the Earth towards it. So what this means is that any two objects, no matter how light, they're going to experience a pull on each other. So even if you have a feather, right? Even if you have something as light as a feather and a tennis ball, these two are going to experience a pull on each other. The tennis ball will be pulled by the feather, and the feather will be pulled by the tennis ball. Now you might think this is absurd. No, of course this doesn't happen. If I put a feather next to a ball, we don't see that the feather is, gravitating towards the ball. That doesn't happen. And the answer is, of course it doesn't. But that doesn't mean that the force doesn't actually exist. Okay? It doesn't happen because there are all sorts of other much stronger forces that are acting on the feather and on the tennis ball. Things like the force of friction, things like the weight as a result of being on Earth, probably the normal force. So there are much stronger forces being applied on these objects as opposed to their interaction as a result of their own gravity. So the gravitational force formula is given by this really neat formula, F equals G m1 m2 over d squared. And what are all of these quantities? So let's begin by describing first of all F. So F is nothing surprising. It is the force of gravity. Now, G, on the other hand, is what we call the gravitational constant. And from the name, it's a constant, which means that it always has the same value. And it's a very, very, very tiny value, which is 6.6 times 10 to the power negative 11. And it has a weird unit as well. It's Newton meter squared all over kilograms squared. And what this means is that whenever we want to calculate the force of gravity, the masses must be very large so that the force can be significant, because the gravitational constant is extremely tiny. And why is it tiny? This tells us that the gravitational force in general is a very weak force. And that's why we need very large masses that will end up multiplying with this very tiny number so that the force ends up being a significant number. If our masses are small, then that means multiplying them with the gravitational constant will make our gravitational force extremely small, which means that we will not see clearly the effect of these forces. That is why, for example, if you have a feather, right, and if you have a little tennis ball, these masses are very small. Multiply them with the gravitational constant, which is extremely tiny already, and you're going to get a force that is extremely, extremely small. Even with something that weighs only 1 kilogram, right? Even with something as that has a significant mass, like 1 kilogram, when it's interacting with something that also has 1 kilogram as a mass, when you multiply them with the gravitational constant, the force will still be extremely tiny as well. So you need masses that are extremely large to balance out the extremely small value of the gravitational constant. Something like the Earth, maybe, right? So knowing this, we have M1. So what is M1? Whenever we think of this scenario, think of the Earth and the Moon. And M1 would be, let's say, the mass of the Earth, and M2 will be the mass of the Moon. So this is just one example, but it's not necessarily true in every case, right? So I'm going to drag this formula a little bit lower, and we're going to pinpoint M1, the mass of the first object, and you have M2, which is the mass of the second object. And finally, d squared is simply the distance between the center of mass of these two objects. So this would be the distance. So the distance between the center of mass of these two objects. So looking at this formula now, we can kind of see the relationship between these different quantities. So for example, when the mass m1 increases, what do you think happens to the force? Well, given that the mass is directly proportional to the force, so it's a numerator, that means it's directly proportional to the force. So when mass increases m1, that is going to also increase the mass or the force, the gravitational force as a result of that. Similarly, m2, when it increases, it's also going to increase the gravitational force as well. G cannot increase, it's a constant, so we're not even going to look at it. But when the distance increases, what happens to the force? So when we look at the formula itself, we see that the distance is a denominator, which means that when you increase it, it's going to decrease. It's going to have the opposite effect, given that the distance is a denominator. When it increases, it's going to have an opposite effect on the force. It's going to decrease it. But not only that, but additionally, given that we have a squared here, that means when the distance decreases by a little bit, when the distance increases by a little bit, the force will decrease by quite an amount. So this squared shows us that the distance is the most impactful thing when it comes to the gravitational force. So eventually we say that when the distance increases, the force decreases by an even larger amount. So this is all for this video. In the next video, we're going to see how we can use this formula in order to actually calculate the gravitational force given to two particular objects with their own masses.